Hello guys, and welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. Today, a problem on entropy, a bit of a more advanced problem, but we did solve this problem before in the channel, so I'm going to do a quick review here and try to solve this problem super quickly. If you want to see the full thing, the whole explanation, please check out the previous video on this question, okay? So problem statement reads, oxygen gas is compressed in a piston cylinder device from an initial state of 0.8 meters cubed per kilogram in 25 degrees Celsius to a final state of 0.1 meters cubed per kilogram in 287 degrees Celsius. Determine the entropy change of oxygen during this process, assuming constant specific heats. All right, so please note that we're given a specific volume and a temperature, right? So these states are completely defined. You can find anything you possibly need to find from these states, should we wish. Also, please note that this is oxygen, so it's an ideal gas, right? So ideal gas applies. Ideal gas relationships applies here, all right? So I'm going to go straight off into this idea here. The difference in enthalpy is the integral from state 1 to state 2 of specific heat, dt over t, plus the constant, the ideal gas constant, natural log of V2 over V1. Obviously, this is only valid for natural gas, for ideal gases. And again, you can check the previous video if you want to jump deeper in this. The only thing I'm going to show you here is that we have this term here, and we know that this guy is, if you recall the definition of this guy, oops, this is too thick. If you recall the definition of this guy from previous videos, we've talked about it. It's the change of internal energy with respect to T with the volume constant, right? So this guy is a function of temperature, right? So we would need to integrate this with the changing in temperature. So what we do is we take the average, and we say we're going to take the average so that we can remove this from the integral, and then this whole equation here becomes, a bit simpler because we do average, and thus we simplify our lives a bit. Okay, so to be able to do this average, because this changes of temperature, what we do is we take the first temperature, the second one, and we take the CV as the average being the middle temperature there. So let's start with doing that. What is the two temperatures we have? We have 25 Celsius, and we also have 287 Celsius. So I'm going to sum these two guys up. I'm going to divide them by 2, and that gives me 156 degrees Celsius. So that's going to be the average temperature of this transformation. And I can grab my CV for this out of the ideal gas table for oxygen, right? Note that I need to grab off the table this guy, and probably going to need to interpolate it for 156. I need to grab off the table the specific, I have these two values, so I need to grab off this guy also from the table. All right, last but not least, this integral here now becomes a simple one, natural log of T2 over T1, right? So let's go ahead and substitute that. This is the natural log of T2 over T1, okay? So note that I have the temperatures. These need to be in Kelvin, by the way. I have the specific volumes, which I can see whether they're going to be the same for volume or not. So the only two things I need to grab off the tables are these two guys, and I'm good to go. Right, so let's start with R. I need them to be the same unit, actually. So let's start with this one, and then we'll check out the unit. So I'm going to go to the oxygen table, and I'm going to look for 156. This also needs to be in Kelvin, so 152 thick. 156 plus 273 gives me 429 Kelvin. So this is the temperature I'll be looking for. So 42 ideal gas, air, oxygen. This is what I'm looking for. I want CV. So this is the column I'm interested in right here. Okay, and I want 429. 429 will fall between these two. So these are the two lines I'm interested in. Let's highlight these two. Okay, so I'll need to do a little interpolation to be able to grab the value here. We've done a lot of these in the past, so you can check them out here if you're not sure how to do them. But fact is that I want a value that's going to be between these two fellows here. And when I interpolate, I get this is 6, 8, 9, 7, right? And then obviously the units have to be the same units here. And this is kilojoules per kilogram Kelvin. So kilojoules per kilogram per Kelvin, right? So per change of energy, per change of temperature, sorry. Okay, so I need to be able to, let me copy this, to be able to sum this up there. Okay, where are we? Here. Paste, not there. See if we can paste it in a better place here. Okay, beautiful. Okay, so to be able to, I'm going to plug this guy in here. And know this is a natural log. There's of T over T, there will be no units here. Also natural log of U of V, no units. So to be able to sum, right, to be able to sum, I need this R to be the same unit as this guy here. So I need the R in kilojoules per kilograms per Kelvin. Why am I saying that? Because you could use the generic R, the constant R for all the ideal gases, and that would be per mole, and it would not be per kilogram, so that would do no good. We actually need the one for air. So ideal gas, sorry, air, not oxygen, oxygen. And then I want our constant R, so I want this value here, 0.2598. All right, and note units, kilojoules per kilograms Kelvin. Okay, so I can happily sum up these two values. All good. All right, so I have everything I need. I can go ahead and say, okay, this is going to be 0.897 natural log of, what is my T2? T2 is 200, or is it? Yeah, 287 plus 273. All right, so I have it in Kelvin. What is my initial temperature? That's 25. So 25, that's 298, right? 298. So Kelvin over Kelvin, units go away, plus R, which we just found to be 2598, and then natural log of the volumes. Now, we have this gas in a piston cylinder device, so we don't expect any mass to be entering and leaving. Therefore, the initial mass and the final mass need to be the same. And if that's the case, then the initial volume and the initial specific volume, this final specific volume, they have a relationship between them. So remember that specific volume, let's do it in blue. Specific volume is just a volume divided by the mass, right? I have a relationship that's saying V2 over V1 right here, right? So what if I do V2 or V1 over here? So let's say, okay, so if this is the case, then the volume is simply the specific volume times the mass, right? Okay, so what would happen if I said V2 or V1? Well, this is the same thing as specific volume 2 times mass of state 2 divided by specific volume 1 times mass of state 1. If the masses are the same, these guys cancel out, and then we're left with the relationship that volume 2 over volume 1 is equal to specific volume 2 over specific volume 1. Okay, so I can happily put in here the 0. What was the, oh, this is 0.8 is the bottom one. So 0.1 meters cubed per kilogram divided by 0.8 meters cubed per kilogram. Right, again, units go away. I'm going to be left with the units that we had originally here for the R and the C sub V. And I get that this delta S equals 9.105 kilojoules per kilograms Kelvin. So that's the change in entropy as we go from one state to the other, right? So we're decreasing our entropy when we're going from the 0.825 all the way to the 0.1287. All right, so again, just to stress, I try to do this quickly. If you have questions, you might want to check out the other video, but if you want to put questions down in the comments, that's fine too. If this video helped you out, consider liking it, and we'll talk soon.